Before we start to look at the idea of limits mathematically, let's think about a type of limit that you're more familiar with, and that's a speed limit. Now you know that if you're driving and the speed limit is 60, that you can drive any speed up to 60 miles per hour. You can get very close to 60 miles per hour and still be driving safely. But as soon as you drive more than 60 miles per hour, you're exceeding the limit. And that's a bad thing to do. Here's the mathematical definition of a limit. As x approaches a, the limit of f of x is written L. Mathematically, we write that as the limit as x approaches a of f of x equals L. If all values of f of x are close to L for values of x that are sufficiently close but not equal to a. Suppose we have the line y equals 3x minus 1. So our function, f of x, is equal to 3x minus 1, and we'd like to find the limit of that function as x approaches 2. So what that means is we need to look at points on this graph and think about what happens to the y-coordinates of those points as the x-coordinates get closer and closer to 2. Well, what you can see is that as the x-coordinates get very close to 2 from the left side, the y-coordinates are getting very close to 5. So the way we would write that is this. The limit as x approaches 2 from the left, notice the little minus sign that's just above and to the right of that 2. The limit as x approaches 2 from the left of 3x minus 1 equals 5. So all we're saying is that when we look at points on this graph that have x-coordinates just a little bit less than 2, that the y-coordinates of those points are getting very, very close to 5. Now we could also approach that same x-coordinate of 2 from the right, meaning we're looking at points that have x-coordinates that are bigger than 2. And as we approach from the right, we can see that what's happening is those y-coordinates are getting very, very close to 5. So we would write that this way. The limit as x approaches 2 from the right, see the little plus sign there, of 3x minus 1 equals 5. Now the original problem was to find the limit as x approaches 2, not x approaches 2 from the left or x approaches 2 from the right. But what we have to look at is whether we're going to be approaching the same y-coordinates from the left and from the right of where x equals 2. And we are. The y-coordinates are getting close to 5 from the left and from the right, so we can say that the limit as x approaches 2 of 3x minus 1 is equal to 5. Now what I'd like you to think about is something that doesn't look very mathematical. There's a very famous painting by Da Vinci that's on the ceiling of the Sistine Chapel, and I want you to focus in on a part of that painting that contains the hands. And think about what happens when we look at what's going on between those two fingers. Those fingers are pointing to each other, and they're very, very close to touching, but they're not exactly touching. That's kind of the same thing that's going on when we're looking at limits. We're saying, what happens if we get very, very close from the left? That would be like looking at the left hand. And very, very close from the right. That would be like looking at the right hand. But we're not actually touching. So we're looking to see where those two fingers, where those two sides of the graph are pointing. So look at this particular function. We want to find the limit of that function as x approaches 2 from the left. So what we're imagining is that we're moving along the left side of the graph, very, very close to where the x-coordinates of the points are 2. And the y-coordinate at that point is 3. So the limit from the left is 3. For the limit from the right, we're approaching that point where x is 2 but we're approaching from the right. We're not quite getting there, but we're very, very close. And the y-coordinate of that point that we're getting very close to is also 3. So that means we can say that the limit as x approaches 2 of f of x is equal to 3. It's like the two fingers are pointing directly at each other, and the y-coordinate of where they're pointing to is 3. Now think about the fact that f of 2 does not exist on this graph. There is no point on this graph that has an x-coordinate of 2. We still have a limit as x approaches 2, but we do not have a point that has an x-coordinate of 2. Let's look at this function. This one's called h, and we'd like to know the limit as x approaches 1 from the left of this function. So we're going to think about moving along the graph as close as we can to the point where x is equal to 1, but we're going to approach from the left side. And the y-coordinate we're getting really close to is 4. So the limit from the left is 4. The limit as x approaches 1 from the right of this function means we're going to move from the right as close as we can to the point that has an x-coordinate of 1, and the y-coordinate for that point is negative 2. So what does that make the limit as x approaches 1? Well, since the limit from the left and the limit from the right aren't equal, we're going to have to say that the limit as x approaches 1 of our function does not exist. Now what's f of 1? Well, f of 1 means we're looking for a point on the graph that has an x-coordinate equal to 1. And there is a point at 1, negative 2 that has an x-coordinate of 1. So f of 1 equals 2. So even though the limit doesn't exist, we do have a point that has an x-coordinate of 1. Remember, with limits, we're not actually reaching that x-coordinate. We are approaching it, but not reaching it. And if the limit from the left and the limit from the right are not equal to each other, then the limit does not exist. Here's something called a rational function. We're going to look at the limit as x approaches 2 from the left. Well, from the left side, we would move along our graph looking at points that have x-coordinates getting closer and closer to 2, and you can see that our y-coordinates just keep getting lower and lower and lower, and in fact would never stop. So our limit as x approaches 2 from the left would be negative infinity. Our limit as x approaches 2 from the right means we'd have to look at points that have x-coordinates bigger than 2, but are getting closer to 2. And when we look at that, we can see that the y-coordinates just get bigger and bigger. So the limit as x approaches 2 from the right is positive infinity. And since those two limits, the limit from the left and the limit from the right, are not equal, then the limit as x approaches 2 does not exist. How about f of 2? Is there a point on this graph that has an x-coordinate of 2? Well, in this case, there is no point that has an x-coordinate of 2, so f of 2 does not exist. How about the same function? And we're going to look for the limit as x approaches infinity of our function. So now what we're going to do is look at points that have x-coordinates that get larger and larger and larger. X is approaching infinity. So in order to do that, let's take a look at what happens if we use some values for x in our function and just make those x values bigger and bigger and bigger. So if we use 5 for an input in this function, that's 1 over 5 minus 2 plus 3. That's 3 1/3. If we use 10 for an input value, 1 over 10 minus 2 plus 3, that's 3.125. We can use 100. We can use 1,000. Our x's are getting bigger and bigger. And look at what's happening to our y-coordinates. they're getting closer and closer and closer to 3. So the limit as x approaches infinity of f of x is equal to 3. Another thing you'll notice is kind of interesting about that is that our graph seems to be getting really close to this line x equals 3 as we move further and further to the right. What we're going to find when we start graphing these functions is that that horizontal line is something called a horizontal asymptote. And it's a line that our graph will be getting closer and closer to out on the edges of the graph as x approaches infinity, or in this case as x approaches negative infinity as well. Now this is something called a rational function. And we're going to find the limit of this function as x approaches 3 from the left. Now think about the fact that when x is equal to 3, we've got a little problem with this function, because that would mean we have a 0 in the denominator, which is undefined. So 3 is not part of the domain of the function. But that's not a problem when we're finding limits, because when we're finding a limit as x approaches 3, that means we're not actually reaching 3. So we aren't using input values that are going to make this function undefined. If we use a table of values to see what's happening, and pick numbers out that are to the left of 3 because we're approaching 3 from the left, but are getting closer to 3, and use those as input values in this function, we're going to see what happens to the output values. The value of f of x is getting really close to 6. So the limit as x approaches 3 from the left of this rational function is 6. How about from the right? How could we do that? Well, we can set up a table in the same way. We could think of values of x that are larger than 3 because we're approaching 3 from the right. But we're going to make those values closer and closer to 3. So we'll use 4 for an input value in our function, and we get 7 back out. 3.5 gives us 6.5. And if we keep putting these values in that are closer and closer to 3, the output values we're getting are very close to 6. So the limit as x approaches 3 from the right of our function is 6. And since the limit from the left and the limit from the right as we approach 3 are equal to each other, we can say that the limit of our function as x approaches 3 is equal to 6. The reason we used a table to find the value of this limit is that we didn't have a graph to look at. The graph will make finding the limits pretty easy, but we won't always have a graph to begin with. Sometimes we'll just have the function and maybe we're making the graph. So we're going to have to be able to look at these functions and determine some things about the nature of the function in ways other than starting with the graph. Another thing we talked about was that this particular function is undefined at 3. Because if 3 is used as an input for x, we do have division by 0 taking place. So 3 is not part of the domain of the function, but we still were able to find a limit as x approached 3. If we have a polynomial or radical or rational function, and that function is defined at the value that we are trying to approach when we take our limit, that we will be able to find our limits very easily by simply evaluating the function at that value we're approaching. For example, what if we wanted to find the limit as x approaches 4 of this polynomial function? The function is defined at 4. 4 is a part of the domain of this function. So we are able to find the limit by simply substituting 4 in for the variables. So the limit as x approaches 4 of this function is 11. As we get really close on this graph to the points where x is equal to 4, the y-coordinates will get very close to 11. Here's a radical function, and we're trying to find the limit as x approaches 0 of this radical function. The function is defined at 0, so in order to find the limit, we can simply substitute 0 in for all the x's, and we can find that the limit as x approaches 0 of this radical function is the square root of 2. As our x-coordinates along this graph get very close to 0, our y-coordinates get very close to the square root of 2. And for this rational function, if we're trying to find the limit as x approaches 4, 4 is not a restriction on the domain of the function. So that means to find the limit, we can simply substitute 4 in for our x's, and we'll have the value of the limit. As x gets very close to 4 on this graph, the y-coordinates of those points get very close to 5.1. So let's go back to this function. We've looked at it already, and we found the limit as x approaches 3 by making some tables. And we found out that the limit as x approaches 3 was equal to 6. But we can't just substitute 3 in for the x's in this function to find the value of the limit, because 3 is a restriction on the domain. But what if we try to simplify the fraction by factoring the numerator and then looking for a common factor, and then simplify to just the limit as x approaches 3 of x plus 3. Now we don't have any trouble with 3 not belonging to the domain of the simplified function, so we can just substitute 3 in for the x, and we get the same limit. The limit as x approaches 3 of our function is equal to 6. Now the other thing we're going to talk about briefly is continuity. And to get an idea of what continuity is about, I want to go back to the hands we looked at. And I'd like you to imagine that what we want to do is roll a marble from one hand to the other. If we try to do that, what we're going to see is that we would have something that would be considered discontinuous going on. In other words, if we try to take a marble and roll it from one hand to the other, we've got a problem at the gap. The marble's just going to drop off. We can't get from one hand to the other. So we have, in essence, a hole in our hands, and that hole allows the marble to drop through. So what would this have to look like to not be discontinuous? In other words, to be continuous? Well, in that case, that gap would have to not be between the two hands. And if we had that, we would be able to roll the marble from one hand to the other. Now we're going to see the same thing happening with graphs. And when we're looking at continuity, we're going to have some specific steps that we're going to follow to test our functions to see if they are continuous. So here's what we're going to do. If we have a function and we would like to know if it's continuous at a point where x equals a, then the first thing we're going to do is see if the limit as x approaches that value of a exists. The second thing we're going to do is see if f of that value a exists. And if both of those are true, then we have to see if those values are equal to each other. If the limit as x approaches that value is equal to the value of the function at that same value, then we can say that our function's continuous. So we're going to have this three-step process we follow to determine if a function is continuous at a point. Now, just as an aside, we can also determine if a function is continuous over an interval, and in order to be continuous over an interval, it has to be continuous at every point in that interval. But what we're going to look at right now is just continuity at a point. So let's start with this. Is f continuous at x equals 2? Now it's probably pretty clear from the graph that we have a hole in it. We have a hole that seems to be at the point 2, 3. And if we try to draw along this graph from left to right, we'd have to pick up our pencil at 2, 3 and hop over to the other side of the graph. So it might be pretty clear from the graph that this is not a continuous function. But in order to determine if it's continuous mathematically, we're going to have to first of all test if the limit exists at that point where x equals 2. So if we look at the limit from the left, that equals 3. The limit from the right of 2, that equals 3. So we do have a limit as x approaches 2 of this function, and that's equal to 3. So far so good. The second thing is we have to know whether f of 2 exists, and it doesn't. So because we've got a failure at the second step of this three-step process, we can stop and say f of x is not continuous at x equals 2. So we're going to look at a similar graph, but this one you'll notice has a point at 2, 1. And we'd like to know if f is continuous at x equals 2. So we're going to go through our 3 steps. First of all, determine if there is a limit as x approaches 2 on this graph. And there is. The limit from the left and the limit from the right are both equal to 3. So yes, indeed, we have a limit as x approaches 2 of f of x. The second step is there such a thing as f of 2? And yes, there is. F of 2 equals 1. That's coming from that point that we see. And then the third step is, do those two values equal each other? And they don't. The limit of our function as x approaches 2 was 3. That was not the same as f of 2 because that was 1. So we've got a failure at the third step in our process, which means f of x is not continuous at x equals 2. Imagine if you were trying to draw the graph from left to right. You would draw along the line, you'd get to that hole in the graph, you'd have to jump down and make the point at 2, 1, and then you'd have to jump back up to continue the rest of your graph. So anytime you would have to lift your pencil off the paper to continue the graph, that's where you have a discontinuity. Is this graph continuous at x equals 2? Well, let's go through the 3 steps and find out. First, we have to decide what the limit as x approaches 2 is. So from the left, the limit as x approaches 2 is 4, and it's the same from the right, which means, yes, we do have a limit as x approaches 2 on this graph. The second step is, do we have a value for f of 2? And we do. F of 2 is 4. There's a point 2, 4 on the graph. And the third step is, let's see if those two things are equal to each other. And they are. The limit as x approaches 2 is 4. F of 2 is also 4, so those are equal to each other. So since we have a limit as we approach that value where x is 2, and we have a value of the function where x is 2, and those two things are equal to each other, we can conclude that f of x is continuous at x equals 2. Now we have a little more that we'll be talking about in the next video about continuity, especially when we're looking at functions that are piecewise functions, and we may or may not have graphs, but we still need to figure out if our functions are continuous.